Swayam Prabha. Digital India. Educated India.
Dear friends, today we will discuss about the Bondgraph method of system modeling. In the last class I briefly explained the Bondgraph method, what is the importance of this method and how this method can be used for modeling of dynamic systems. Today we will go into the details of the modeling techniques, what are the important elements in Bondgraph and how do we develop a Bondgraph model for a dynamic system, and then how can it be used for simulating the dynamic behavior. So as I explained in the previous few lectures, we need to model the behavior of systems under various stages of design in order to understand the behavior of the system, how it responds to particular inputs, what kind of controls need to be incorporated and what kind of tuning is to be provided in order to get a desired outputs. We need to use the modeling methods, and Bondgraph is one of the methods which can be easily implemented for system design. As I explained earlier, Bondgraph method is basically used for multidisciplinary systems where you have multiple domains like mechanical systems, electronic systems, electrical systems, software, computers and hydraulic systems. So when you have a system with multiple domains or multiple specialization, we need to have a common language to model them, and Bondgraph provides you this common language which actually across the domains we can use the same kind of elements to model the system. That is one of the advantages of using Bondgraph methods. So as I explained in the previous class, this actually discusses about the exchange of power between two parts of a system. So whenever there is a dynamic behavior of a system, there is an exchange of power between elements. So we are trying to model this power transfer or movement of power or the transaction of power, and that is why sometimes it is known as power Bondgraph method also. And here the flow of power is represented by a bond is represented by a half arrow. So that direction is represented by the arrow and flow is represented by a bond. And as I mentioned, effort and flow are the two components of power. In this diagram I explained the difference between the normal or conventional way of modeling and the Bondgraph modeling. So here basically we do not go for the differential equations, instead we directly go for the Bondgraph model. So direct from the physical system we develop an engineering model of the system and then convert that into a Bondgraph, and then we can use the standard software for simulation. So that is the main difference in Bondgraph and the classical approach. So we will actually jump through this differential equation, we do not go through the differential equations, we will bypass this because the creation of equations and the block diagrams will be carried out by the software itself. So we have standard softwares to do the job. Again coming to the generalized variables for the system, we have two important variables, one is known as the effort, the other one is the flow. Effort is normally represented by E and flow is represented by F, they are time dependent variables, so we will write as ET and FT. So these two variables actually represents the flow of power. The power is obtained by multiplying this effort and flow, so that actually defines the power transfer between two elements. The other two variables are momentum denoted by Pt and displacement denoted by Qt. So you can see here the momentum is represented by P and displacement by Q, and they are not independent. The basically P is an integral of effort, so P is obtained by integral E dt and Q is integral F dt, that is the integration of F will give you the displacement, integration of effort will give you the momentum. For example, if you have F is the velocity, then the integration of velocity gives you the displacement. So that is the relationship between the variables F and Q and E and P, and the power transfer is Et multiplied by Ft. So these are the 4 generalized variables used in modeling. to explain the energy flow, so the energy flow is represented by, as I explained, by a bond. So they are known as directed harpoons. So the energy flows are represented as directed harpoons. The two adjugate variables, that is the effort and flow, are annotated above and below. So the E is actually above the bond and F is below the bond, or the other way you can say that the hook of the harpoon always points to the left and the term above refers to the side with the hook. So when this is the harpoon and this is the hook and this is on the above and this is below. So when it is in the vertical direction, then E will be on the left side and F will be on the right side. So this is the normal convention of representing effort and flow. For various domains, for multiple domains, this effort and flow can be defined. For example, for electrical, effort is voltage and flow is current. For translational motion, force and velocity. Rotational motion, torque and angular velocity. Hydraulics is pressure and then volumetric flow. Chemical is chemical potential and molar flow. Thermodynamic is temperature and entropy flow. So you can see here, for various domains we can still have the effort and flow parameters, whether it is electrical system or hydraulic system or a chemical system, you can actually represent the effort and flow irrespective of the domain. So we do not need to worry about the domain, because the effort and flow is always the same representation can be used to represent a voltage or a pressure. So E will be the common for voltage or pressure. So even if there is a change in the domain, still the E and F, the representation remains the same. So that is the advantage of using Bondgraph. Now there are some basic elements in Bondgraph modeling. So these are the most basic building blocks for making the Bondgraph. The first element is the inductance or I. So this is actually represents, the I element represents the electrical inductance or mechanical mass or inertia. So any electrical inductance, mass or inertia can actually be represented by an element I. So that is shown in the diagram here. So this is the representation of an I element. So you have this I and then a bond representing the I element. Then the another element is C, or the capacitance. So this is known as inertial element, or this is the capacitive element. So this is actually for electrical capacitance or mechanical compliance. So if you have a spring or a electrical capacitance, that can actually be represented by a element C. And then R for electrical resistance or mechanical viscous friction, that is the resistance element R. So these are the three basic elements of Bondgraph, I, C and R. So I represents the inductance or mass or inertia, C represents the capacitance or compliance, R represents the resistance or friction forces. So these are the three basic elements, and then we have some other elements called TF. TF represents a transformer. So whenever there is a transformation of energy from one form to other form, or some rotary motion to linear motion, or you can have a gearbox where rotary motion is transformed to another rotary motion with a ratio of power, then we can represent it by an element called TF. So here you can see the TF is E1, the flow is E1 and F1 are the inputs. So effort 1 and flow 1, then you have effort 2 and flow 2, and this TF M represents the transformer ratio. And the relationship between E1 and E2 is given here. E2 is equal to 1 over M E1 and F1 is 1 over M F2. That is the relationship between E1, E2 and F1, F2. So here E1 is converted to E2 and F1 is converted to F2 through a transformer. You can think of a gearbox where there is a change in speed as well as a change in torque after the before and after the gearbox. So that relationship can be represented using a element called TF, and the gearbox ratio can be represented as M, the ratio of gears represented by M, and the relationship E2 is 1 over M E1, or we can say E1 is equal to M multiplied by E2, and F2 is 1 over M F2, F1 is 1 over M F2, or F2 is equal to M F1. And there is another element called gyrator. This is actually different from a transformer. So in this case the relationship is between E1 and F2 and F1 and E2. Basically the effort is converted to a flow and this flow is converted to an effort. That is why we use a gyrator. For example, if you have an electric motor, so we give a current and you will get it as a torque output. So the flow parameter is converted to at the torque parameter. So here is a conversion from flow to effort. So that kind of relationship is represented using a gyrator element. So we can see E1 related to F2 and F1 to E2, and that relationship is given as F2 is 1 over d E1 and F1 is 1 over d E2. So we are relating the F2 and E1 and E2 and F1. So that is the relationship for gyrator. And there are two other elements, source effort and source flow. Source effort is effort source, that is you provide a effort to the system as a source effort, then that is represented by an SC element. For example, a voltage source can be represented by a source effort. So here the source is the effort and that is given to the system, then you represent that as a effort source. Then you have a source flow or the flow source, which is represented by SF, where you have a current source or a flow source like a hydraulic flow or any other flow input, then we represent it as an SF. So you have source effort and source flow, which represents the sources for the system, that is the input sources to the system, an effort source and a flow source. Then you have a gyrator, which represents the relationship between the effort and flow, and then the input effort and the output flow, similarly input flow and the output effort. So that can be represented using a gyrator element. And then you have the transformer element, which actually relates the efforts, that is E1 and E2 and F1 and F2, and we have other power consuming elements I, C and R. So I, C and R are the power consuming elements, these are the power transfer elements, and this is the source effort and the source flow elements. So these are the basic elements needed for bond graph modeling. We have two more elements which actually represents the junctions in the bond graph. So whenever you have a junction, that is whenever you have different sources coming to one point and then it gets separated, so that can be represented using bond graph junctions. So we have two kinds of junctions, one is known as a 0 junction, the other one is a 1 junction. So you can see here 0 junction and 1 junction. The 0 junction is known as a common effort junction. So the 0 junction, we say this is a common effort junction because all the efforts are equal in this junction. So we have 1, 2, 3, 4, 5 bonds here, and these 5 bonds, all these bonds are having same effort. So E1 is equal to E2 is equal to E3, E4 equal to E5. So here you have all the efforts equal and the flows sum to 0. So the flows coming inside, so this arrow represents the flow is coming inside. So 1 and 2 are coming inside and 3, 4, 5 are going outside. So whatever the flow is coming inside should be equal to flow going outside, that is F1 plus F2 is equal to F3 plus F4 plus F5, that is the flow sum to 0. So that is the 0 junction. So you have a common effort and the flows adds to 0. This is something like you have a voltage source, many elements are connected in parallel to that voltage source, then you will be getting same voltage drop across all the elements, but the currents will be different. So this actually represents that kind of a scenario. Then you have another junction called 1 junction. The difference between 0 and 1 is that 0 is a common effort junction, but 1 is a common flow junction. Here you have the flows are equal. The flows in these 3 bonds, that is 1, 1, 1, 2 and 1, 3, they are all equal. So F11 is equal to F12 is equal to F13. So all the flows are equal here and efforts sum to 0. So E11 plus E12 is equal to E13. So you can see this 11 and 12 are coming to this junction and 13 is going out. So you have E11 plus E12 is equal to E13. So that is the 1 junction. Now with these elements, that is 0 and 1 junctions, and you have the source effort and source flow, then you have the transformer, gyrator and I, C and R elements. So these are the only elements you need to make a bond graph model of any system, whether it is electrical system, mechanical system or hydraulic system or a combination of these. We can model the system using only these elements. So we have 3 power consuming elements I, C and R, then we have the transformer and gyrator, and then source effort and source flow, and 2 kinds of junctions 0 and 1. With these elements we can actually model the complete system using Bondgraph methods. We will see few examples how do we do that, but before going to that we have one important function to be defined, which is known as the causality in the system. So causality basically it actually explains what actually causes the system to perform. So whether there is a input is effort or a flow into that system which actually causes the system to behave. So that is known as the causality. So every bond defines two separate variables, the effort and flow, and consequently we need two equations to compute values of for these two variables. So we need to have two equations for effort and flow. It turns out that it is always possible to compute one of the two variables at each side of the bond. So you can actually compute one of these variables at one side of the bond, and a vertical bar symbolizes the side where the flow is being computed. So here you can see that a vertical bar is shown to show the causality. So wherever this vertical bar is shown, it shows that the flow is calculated on that side and effort is coming on this side. So here flow is calculated this side and effort is on this side, that is the representation for the vertical bar or the causality of the bond. There are mandatory causality for sources like TF, GY and 0 and 1 junctions, and there is a desired causality for C and I elements and free causality for R element. I will explain this, how do we actually give this causality shortly. So here is the explanation for causalization of the sources. So now we have this SC and SF. SC is the source effort and SF is the source flow. So the flow has to be computed on the right side because effort is coming here. So we need to calculate what is F. So F is calculated based on the effort. So you have the effort and it is calculated based on what is the effort coming here. Calculate F is equal to a function of the effort. Similarly here source flow, so the flow SF, so the causal stroke is here, so therefore the flow has to be calculated here and effort is to be calculated here. So the source computes the flow, here the source computes the effort. So the source computes the effort here and here the source computes the flow. So that is how we give the causality stroke, and these are the mandatory causality for source effort and source flow. So for the source effort you will always have a causal stroke here, and for the source flow you will have a causal stroke here at the other end or the left side of the bond. So here the causality of the sources is fixed, SC and SF. You cannot change the causality because here the source computes the effort and then here the source computes the flow, that is why it is already fixed. And for other elements, to fix the causality for the other elements we need to actually find out the relationship for these elements. So here you can see this is the R element, and for R element you can actually have a relationship like U is equal to R multiplied by I or I is equal to U divided by R. That is how you calculate the, so here U actually represents the effort and I represents the flow, that is the voltage and current. So now you can actually supply a current to this element and get a voltage drop. So I is given as an input and R is given as the output. So actually you can calculate U is R multiplied by I, that is the relationship for this causal stroke. So in this case the causal stroke is on the left side, then the relationship is U is equal to R I. If the causal stroke is on the right side, then the relationship is that the I is computed, U is the input, so you are giving a voltage to the resistance and then you are getting a current flow output. So I is equal to U divided by R. So here we are calculating I on this side and here we are calculating I on this side. So that is I is U by R. So if you are calculating it on this side, then this I is U by R and here it is U R multiplied by I. So the causality of resistor is free. So depending on the situation you can actually provide the causality on this side or this side because it is free causality for R element. Then coming to the C element, here actually you cannot have various causalities because you can have only one kind of relationship. Here you can see this is a differential relationship, du by dt is equal to I over C. So normally we can actually write it as the 1 over C integral of u dt as I. So I is equal to 1 over C integral of u dt. So that is the relationship you can actually find for this. So in this causality you will be getting an integral relationship for the I. We should not go for the differential relationship. If you have a differential relationship it is difficult for us to visualize the system and therefore we go for an integral causality, and integral causality actually gives a stroke over here which actually tells us that the effort or the U is 1 over integral C dt. So we can actually find out the output using the integral relationship. And similarly you can actually for the inertial element also you can go for the integral relationship where U is obtained as 1 over I integral I dt. So the flow is obtained as integral of I dt 1 over I integral of dt can be obtained. So that actually gives you an integral relationship with this causality. I will explain it a little bit more when we take some examples. So you can understand that this is the integral causality for C and this is the integral causality for I. So here actually the I calculation is represented here. So the I is actually obtained as integral of 1 over I U, and here U is obtained as integral of 1 over C I, that is the flow. That is the integral causality for these two C and I elements. Of course in some cases you may find that there becomes a differential causality, but then there are methods to solve that one by providing some additional elements, but in normal cases we always try to provide a integral causality for C and I elements. That is about the causality of R, C and I elements. So this is the relationship for I, F is 1 over I integral E dt, something similar to the relationship F is equal to MA. So here F the flow is equal to 1 over I integral E dt. So the flow is calculated here. So the effort is the input, so the effort is coming here and the flow is calculated here. F is 1 over I integral E dt, that is the integral relationship you are getting. And for C elements you can see the 1 over C integral F dt is the relationship, that is the flow is calculated here. So effort 1 over C integral F dt gives you the effort relationship. So E is equal to 1 over C integral F dt, that is the relationship, and this integral causality is preferred when given a choice. So whenever you have a choice you should try to go for the integral causality for these elements. And the final one is the causality for the junctions 0 and 1 junction. As I told you, 0 junction is a common effort junction. So there can be only one effort coming into the block to this junction, and therefore you can see that this is the effort coming where the flow is calculated. So this is the effort coming in that one stroke over here, and all other bonds will be without a causal stroke on this end, then they will be having causal stroke on the other end. So that is the causalization of 0 junction. So the junctions of type 0 have only one flow equation, and therefore they must have exactly one causality bar, because this there can be only one flow equation, that's why this is actually one stroke over here. And for the one junction, the junctions of type 1 have only one effort equation, and therefore they must have exactly n minus 1 causality bars. So here you can see there is only one flow, and there is it is a common flow. So one flow coming inside, and then that is common for all the others, therefore you will be having causal stroke on all other bonds near to the junction, and one without any causal stroke. So that is the causality for one junction. So you can see that F1, F2, F3 are equal, and E1 is equal to E2 plus E3, because this is input effort, is the output. So E1 is equal to E2 plus E3, that is the causal stroke for causality assignment for 0 and 1 junction. So we have fixed causality for source effort and source flow, then we have preferred causality for I and C elements, and we have a flexible causality for R elements, and we have fixed causality for 0 and 1 junctions. Now the last one to be seen is the TF and GY elements. So the TF and GY, it is not on here in the slide, I will explain it to you using the boards. So we go to the board and then see how do we actually represent these elements and develop the Bondgraph model for physical systems. So as I explained, we have this I element with a causality like this, and then we have this C element with a preferred integral causality, so C element, and then we have an R element. So you can have a causality over here, or you can have it here depending on the situation, and then we have this source effort. So this is the source effort, and then you have the source flow, and we have these junctions. So we have a one junction So in one junction, as I told you, it is a common flow junction. So you can actually have one flow, there is only one junction, so there can be only one without a causal stroke and all other will be having causal stroke at this point. And then you have this 0 junction. So here can have only one effort and all others will be here. So this is the one junction and this is the 0 junction, and the other two elements are the transformer and gyrator. The transformer, you can have a causality like this, either like this, that means the effort the flow is calculated here and flow is calculated here, or you can have a causality here also. So any one of these. So if this stroke is on this side, then here also it will be having on this side. So you can have either this or you can have this for the causality for transformer. And for gyrator, it will be like this. You can have a causality like this, because here actually the effort is converted to flow here, that is why you can have it here. So this is one possible causality, and the other one is this one, you can have a causality like this also. So you can have a causality like this or you can have a causality like this for gyrator. So depending on the situation, you will have to identify what kind of causality exists for that particular element, where it is connected to, which junction it is connected to, or which element it is connected to. Accordingly we have to assign the causality for these elements. So these are the basic building blocks for the Bondgraph modeling. Now let us take a very simple example and then see how do we actually develop the Bondgraph model for such systems, for mechanical systems or hydroelectrical systems. Let us take the simple example shown in the slide. It is basically a mass spring damper system. So you can see here it is subjected to a force, and then this is the displacement xt, and if you can assume that there is a reference velocity also xr t. Of course if it is fixed then it will be 0, otherwise it can be actually represented xt and xrt as the reference, and this is the mass and this is the spring constant k and this is the damping coefficient b. So this is the mechanical system. If you want to develop a Bondgraph model for this, we know that if you do for a mathematical modeling, we have to write down the equations mx double dot, assuming this as 0, you can write it as bx dot plus kx is equal to f. We can write this is the equation, and then we need to simulate it and then find out the output. But in the case of Bondgraph, we do not need to really go for the mathematical equations. We can actually directly write down the Bondgraph, or we can make the Bondgraph and then directly simulate it. How do we do this? Basically we identify there is a force input to the system. So we will write down that as a source effort. So we know that a force input is a source effort. So it is an effort which is given as an input. So this is a source effort and we have a causality over here. Now for the time being I am assuming that it is 0, there is no velocity over here, that is 0. So I do not consider that part here. Now I know that this mass, this force is acting on the mass, and then it is having a velocity displacement x, which actually we can write x dot is the velocity here, and then this k is having a displacement. So this is actually, this spring is subject to a displacement of x and b is subject to a velocity of x dot. So we are having only one velocity here, which is actually the x dot is the velocity. So we have a common velocity here, which is actually k and b element are subjected to, therefore we will be having a one junction over here because there is a common velocity junction. Now we look at, okay, now there is a common velocity here and there is a mass attached to this. So we write down, we make a bond for the mass, that is I element which is equal to m, and then it is connected to K and B, the same velocity. So therefore we can actually connect it to a C element which actually represents the spring stiffness, and then we have a R element which actually represents the damping in the dashboard. So that is all what we need to do. We have completed the bond graph model for this system, and what we need to do is to just give the causality assignment. We know that I has got a fixed causality, as you can see here, I has got a fixed causality, and then I has got a causality, fixed causality, C has got a fixed causality, and then R can be given like this, because one junction can have only one bond without a causal stroke at this point. It is a common velocity junction, and this velocity at here is the x dot. X dot is the velocity at this junction. So we have this source effort, so we know that this is a force coming, and then this is the R, this is the effort, this is the velocity of this coming. So here it is x dot is 1 by, so this flow, so we have an effort coming here. So if I number this 1, 2, 3 and 4, I can write it as E1 F1, E2 F2, E3 F3 and E4 F4. I can calculate F2, F2 is nothing but 1 over m integral of E2 dt. So that is the velocity or F2 here. F2 is nothing but x dot. So we have this F2 which is nothing but the junction velocity x dot. So x dot is calculated, and then all others are because of this. Now we know the x dot or this F2, F2 is equal to F3 is equal to F1, sorry, yeah, F1 is equal to F2 plus F3, F1, F2, F3 are all same. So we have all the flows are equal here. So we have this relationship, and now we know what is E3, we can actually calculate what is the friction forces here. E3 is nothing but 1 over C integral F3 dt, and similarly V4 is R F3, so integral, sorry, R into F4. So that is the relationship here. So we know that all this effort can be calculated E3, E4, and we can calculate the flow also. That means once we know this bond graph, we can actually calculate all the parameters, that what is the velocity of this, what is the displacement and velocity of this mass, what is the force acting on the spring that is obtained by here, this is the force acting on the spring, and what is the force due to friction, again we are getting E4 is RF4. So all these parameters can be easily calculated using the bond graph. So our modeling is completed, and once we have this model, we can actually use any software for bond graph. There are few softwares available. One is known as Symbol, it is a software available. Then there are other softwares also. There is another called 20sim. These are all commercially available softwares which actually can simulate this bond graph. So what you need to do is just give us an input to the simulator, then it will calculate all these parameters, and you can actually connect an integrator to this junction, and it will give you the displacement x. So here is x dot, so you will be getting the displacement x from this integrator. Though it was a very simple system, we can show that just by looking at the physical elements, we can directly convert that into a bond graph. So we do not need to worry about the equations. So these equations are all explained for understanding. Basically what we need to know is how it is connected, how many junctions are there, and accordingly we just connect the elements and complete the bond graph. That is all what we need to do in modeling the system. So that is a simple example for a mechanical system. In the same way, we can actually model electrical systems or hydraulic systems also. I will take a simple electrical circuit and show how this can actually be, bond graph can be used for modeling this. I will take a circuit. So we have a current source, so I will show it as a current source, and then I connect various elements, a resistance here, a voltage source, then a capacitor, an inductor, a resistor, like this. So we can see there is a current source and there is a resistance, I will put it as R1, and this is C, this is R2, this is an inductance L, and there is a voltage source, some voltage source. This electrical system can actually be again modeled using Bondgraph. We can identify the sources. So we have a current source here, and we know that there is a current flow in this one, that is represented as I1, and again there will be a current because of this battery source, we can represent it as I2, and we are having another I3 here. We have three currents, I1, I2 and I3 in this circuit. We have a current source here. Now to model this one, we know that there is a current source, so we start with a SF element. So an SF element represents the current source. So this is the current source SF and its causality is like this. So we will have a R1 here attached to this one. So this is R1 and a 0 junction, because this actually R1 is subjected to I1 and I2. Basically I1 minus I2 will be the current flowing through this, because in the different direction. So that actually to be represented. So there will be a common effort junction here to represent the flow of current I1 and I2 onto this element R1, and then we will have a source, we an I2 current source, and we have an effort source coming. So we have an effort source, that is SE, a voltage source acting, and we have a current flowing from this, and that is this I2. Here there will be an I2 here, and then we have this C2 element, that is the capacitor C2, C element, and then we have I3, that is a one junction where we have this I3. So here this I2 and I3 here, and this is attached to the R element and or the I element. So I is the L element or the inductance. So this actually completes the Bondgraph model for this circuit. So you can see here, of course we can actually represent here at a one junction and then as a 0 junction, but I put it as like this. You can actually put it like this also to represent this is I1, this is I2 and this is I3. So we can have three one junctions can be separately shown, but when we simplify it, it actually automatically become this one junction will be removed. That is why I did not show it first initially, but you can actually represent this as I1, I2 and I3, three one junctions, and then we have this R element which actually is a summation of I1 and I2, or the R will be subjected to I1 minus I2, and similarly the C will be I2 minus I3. You can see I2 minus I3 will be acting on this, and this will be subjected to I3 only, this current only. L and R will be subjected to current only. So this actually gives you the Bondgraph model for this electrical circuit. Again this was a simple circuit, but if you have any complex circuit or if you have a mechanical and electrical system combined, still we can actually develop the Bondgraph model. Simply by looking at the physical system you can develop the Bondgraph model. We do not need to worry about the equations, and once we have this model we can directly use it in a software to get the output. Whatever the output you want to find out the voltage across this one or the voltage drop or the current flowing can be easily obtained from this one. And again you can actually assign the causality also here. This is causality here, and then this is the causality, and the C has got this causality, and you have SC has already got the causality, and R will be having this causality. This is one junction, so you will be having this causality here. So this is the way how we actually develop the Bondgraph model for electrical and mechanical systems. We can actually develop the write down all the equations and develop the state space model for this, but the objective of this lecture was basically to introduce the topic to you, not to give a detailed description of how the Bondgraph method can be used for modeling the system, but just to tell you that this is one of the easiest and good methods for modeling mechanical system or multi-domain systems which can actually give you the performance of this system from the Bondgraph. Let me go through briefly some of these models I already explained. So this I already explained about this spring mass damper system. So the finally you will be getting a model like this and the equations can be written from this. Once you have this model you can actually feed it into a software and you can get all the performance characteristics. If you know the values of R, C and I and the force you apply, you can actually plot all the performances using the standard simulation software. You can get the position, velocity and any other parameter you want, you can plot, you will be getting responses something similar to this. Just to tell you how Bondgraph can be used for very complex systems, you can just look at this model. This is actually an underwater robot. It has got many complex dynamics, many subsystems and its own dynamics. So if you want to represent the complete dynamics of this underwater robot, we can use the Bondgraph method and develop the Bondgraph model for this and can be used for simulation also. I am not going to explain how it is being done, but I can just show you how it will look like. So the Bondgraph model for the AUV will be looking like this. Some of the elements are not familiar to you, like these are all vector bonds because we have 3-dimensional representation or they have 6 degrees of freedom motion for the robots. So we need to represent those parameters like angular velocity and linear velocity in 3 directions. So if you want to represent that, we need to go for vector bonds, and so if you use vector bonds you will be getting this kind of a bond graph for the robots, and we can simulate it also and find out what will be the responses. And to make it a little bit more complex, if you have a manipulator attached to this robot, we can again still represent the complete dynamics of the robot as well as the manipulator and then find out the response of the manipulator under various scenarios. So the bond graph will be looking like this. This part actually represents the AUV or the underwater robot dynamics, which actually like this here just for representation, and this actually shows the its dynamics or the bond graph model of its dynamics, and this shows the 3 links of the manipulator. So this is the first link, second link and third link, and you can see the interactions between these links as well as the robot and the manipulator and the AUV can be shown like this here. So this actually represents the complete dynamics of the AUV and the manipulator using bond graph methods. So to summarize, we have many advantages and disadvantages for using modeling and simulation in system engineering. Basically for various stages we need to use the modeling and simulation tools, and we discussed a few of the tools which can be used. There are many other tools also, probably you can actually get more information from resources, but the advantages are basically we can do virtual experiments without much of resource requirements. So if you have a model, we can actually simulate it and find out the behavior without really constructing an equipment. And some system states cannot be brought about in the real system, or at least not in a non-destructive manner, like crash test and other deformation test cannot be done without destroying the equipment or destroying the sample. So this kind of scenarios can be easily modeled and simulated using simulation tools. All aspects of virtual experiments are repeatable, something that either cannot be guaranteed for the real system or would involve considerable cost. So the repeatability is an important aspect of modeling and simulation. And simulated models are generally fully monitorable, all output variables and internal states are available. So unlike the real systems where actually you cannot monitor all the parameters because we may require hundreds of sensors to do that, but in the case of model we can actually monitor most of the parameters very easily. And in some cases an experiment is ruled out for moral reasons, for example experiments on humans in the field of medical technology. So in such situations also the modeling and simulation comes as a very good tool for designers. Of course there are few disadvantages. Each virtual experiment requires complete, validated and verified modeling of the system. So this is one of the biggest challenge. How do you make a complete model and how do you validate the model and verify the model, whether it represents the actual system or not. If it is not representing the actual system, then all your output will be wrong and you cannot make any inferences from these results. The accuracy with which details are reproduced and the simulation speed of the model is limited by the power of the computer used for the simulation, and again power of the computer actually has got some limitations, and then that actually limits your experiment, the simulation experiments. So these are the disadvantages of using modeling and simulation. Okay, so to conclude this lecture on modeling and simulation, we discussed about the importance of modeling and simulation in system design. We discussed a few methods like mathematical modeling, then data modeling, process modeling and behavior modeling, and in data modeling we saw various methods, and then process modeling as well as behavior modeling also. We discussed various methods being used by system engineers during various stages of design process. And then we discussed about the dynamic system modeling, especially when looking at the dynamic behavior of mechanical systems or electrical systems or a combination of these systems. We saw there are few methods to do that. Mathematical modeling can be used, or we can go for physical system based modeling like Bondgraph methods. So the Bondgraph method actually helps in modeling and simulation of multi-domain engineering systems. That actually concludes this lecture on modeling and simulation. Whatever we discussed, it is not complete. We have so many other modeling methods and modeling techniques used by various engineers and in various industries, but this actually gives you a brief idea of how the modeling tools help the system designers in designing their systems and optimizing the system behavior and refining their designed systems. So in the next few lectures we will discuss more about the other aspects of system design, basically looking at the reliability of engineering systems as well as decision making under uncertain conditions. What are the parameters we need to consider when we make some decisions in respect of engineering system design. So these things we will discuss in the coming lectures. So till we meet, goodbye to all of you.